Good morning, good evening, good afternoon to everyone. So welcome for today's panel. My name is Ilaria Parrella. I'm a mission abatement leader in Hughes, and today I will be the chairperson for this panel. So it's a pleasure to participate in the discussion with other colleagues that are here in the panel, and also to welcome all of you in this event. This is the second event for the year 2024 and is mainly a technical webinar that Methane Guiding Principle organized to create awareness about methane emission solution. So today we will discuss about engineering solution to create awareness and to give, let me say, an overview and sharing experience in this space. So first of all, I would like to introduce, I have a pleasure to introduce the other panelists. So first, Clayton Nash from Tegre Corporation. So thank you, Clayton, to come here. Clayton is the Director of Emission Solution. Audrey Mascarenhas, that is the President and CEO of the Questor technology. Thank you, Audrey, to join. And Glen, that is emission management consultant in Schlumberger. Thank you, Glen, to come here. So before to move on the discussion, I would like to introduce a little bit MGP. So as for everyone, we know that Methane Guiding Principle has been launched in 2017, and this is enabling action in industry and the government for methane reduction, methane emission reduction in worldwide, mainly for natural gas supply chain. So there are the members at the moment are 47, and of course we invite all people that are interested to join to participate actively in the conversation and to come with us. Mainly the foundation is to drive through 5 principles the effort in priority area where we discuss and we act on methane abatement. So today, the main topic, as I mentioned, would be the technical session related on engineering solution in different areas where we can discuss methane emission. Mainly, I would like to introduce, let me say, the agenda. So we will spend 30 minutes on some questions that I will moderate with the rest of the colleagues. And later on, we will have other 30 minutes where you can actively participate. So I will suggest all of you to post your question in the chat and to let me say, to participate on any curiosity, any doubt, any, I would like to say, sharing experience that we have on the topic. So I will go through the question later on, and I will involve the people, the panelists in the discussion for those. So I think we can start. So the main I would like to say highlights is that let me stop the sharing that I can see also the panelists in the video, and I hope that everyone can see them. So as I mentioned, methane gas it's a critical because, as you know, lives in the atmosphere more quick than carbon dioxide, and he remains in atmosphere 85 times more than CO2. This is impact a lot the climate change, and I hope that all people here, let me say, knows that this is mainly the priority globally to reduce emission of methane, because it's more dangerous and also can impact more than other molecules in the atmosphere and in the warming, in the world warming. So as also we discussed in other technical panel, so 1/3 of the methane emission are coming from energy sector. So today, with the Glen, Audrey, and Clayton, we will tackle in the discussion how we can contribute on engineering solutions to reduce those for the sector that all of us we are operating. So I think that it's better to start and focus on the topic. And for this, I would like to start talking about venting. Venting is one type of emission. So in the recent International Energy Agency report is explained that 40% of oil and gas emissions are coming, let me say, from this type of emission, and also are not net cost. So that I would like to say that more than 50% of those emissions are methane. So Audrey, talk about venting and considering your experience. What are the technologies that we can explain are being effective in the North America and can be also mobilized globally?
Thank you. So when we look at venting in oil and gas, it really comes from two predominant sources. And we talk about it as routine and non-routine. The non-routine are vented occurrences, oftentimes coming from maintenance, could be upsets or equipment failure. And so sometimes there's not a lot of choice, and we end up putting a lot of methane into the atmosphere for a short period of time. So that's typically what's referred to as non-routine. And then, of course, routine is what's coming from our facilities, whether it's coming off tanks. There are a lot of technologies focused on both of them. I'll first start with non-routine. Because they're short duration, tend to be high volumes, probably one of the most effective ways is to either try and capture that gas, and we've got portable CNG, some different ways. The other area that a lot of clients are starting to use is to maybe make sure it's cleanly combusted. Because methane's so much worse than CO2, by converting the methane to CO2, you actually have a 90% reduction in your greenhouse gas emissions at a very low cost. When we look at facilities and look at the routine that comes from there, it's starting from the bottoms up and looking at what can we do with tanks. We know that engines and compressors need maintenance. Can we design our systems to pick up those volumes in a safe way? Now there's vapor recovery units, there's pull down compressors, there's lots of different technologies available. So the question really comes down to what is the business case? What makes the most sense? And it's not one size fits all. You'll have to really look at where these are occurring, how frequently they do, but there is a lot of technology to allow these volumes to be safely dealt with and not put into the atmosphere.
Thank you so much, Audrey. So based on what Audrey says, so of course, venting is a critical, business case is a critical, but another sector, let me say, an application that is critical is unlit flare methane source. So Clayton, for your perspective, so what solution, let me say, have proven to be efficient in this space? Can you share your tip on this?
Yeah, and thanks for having me, Ilaria. Nice to be with Audrey and Glen. The seemingly obvious one that people talk about is a good quality flare. And so what a good quality flare looks like is something that's designed for the process that it's going to be in and has the right rangeability, the right turn down ratio. And modern flares are going to have features such as variable velocity tips that will ensure adequate combustion and a range of flow rates and are less likely to blow themselves out. So that's a common problem with flares is if they're operating at a lower flow rate, the pilot can be lit and everything's working, but then a large surge in flow rate can actually introduce so much velocity that the flare goes out. And so a robust flare design can reduce the likelihood of that happening. And something that we've known about, we've had the capability for a long time, and we're just now starting to integrate on a broader scale, is effective monitoring of flares. So moving away from just looking at pilot status remotely, but looking at flare temperature, looking at flow rates going to flares, use of more practical flow rate measurement techniques using thermal mass flow meters as opposed to differential pressure meters that have a large, they're actually less accurate, but they have a larger range and less likely to malfunction. And I would say on an organizational level, making it important to monitor these and set up alarms, set up response, so that you're not waiting for someone to physically see that a flare is unlit. One common problem has been, especially in the upstream sector, flares that are intermittent. The flare will come and go, and so when someone sees the flare not lit, they don't think anything of it. So having that remote monitoring where people are watching minute by minute data, every aspect of what's happening with the flare and everything upstream of the flare, so they know that it is lit. If it's not, there can be a quick response to get it lit and mitigate the venting. Yeah.
Thank you, Clayton. Thank you for this perspective. I think you mentioned upstream, and another interesting space is a midstream as well for venting, especially for maintenance that Audrey also mentioned. So I think we need to consider also robust gas during the maintenance for midstream. That is another application for venting. So moving on flaring, you mentioned, Clayton, flaring, and I think the main source of methane emission is a flaring. So there is a global commitment on the zero routine flaring in 2030. Different states, 360 states already signed this commitment, 58 oil and gas companies as well. So there is a global pledge, let me say, to move in the direction to have zero flare in 2030. So Glen, I would like to understand your perspective, especially for the size of flare that are in the range of 1.5 million scarf day. So because in this range, if I'm not wrong, the 90% of site represented by this kind of size. So we are talking about a very spread and very important flare size that we need to abate. So can you give us more details about abatement and monetization of this source?
Yeah, sure thing. So discovering the solutions for flare elimination that minimize and bring highest return on the investment, it's a topic that we get asked about often, and there are many options available, and usually we divide the solutions into four main categories. And the first is power generation, which is either to local use or larger connected grids. Second is separation and compression to products like compressed or liquid or liquefied natural gas, plus condensate. And the amount of condensate, which is the heavier hydrocarbons in the gas that drop out as liquids as you're doing the compression, is dependent on how rich the gas feed is, and it can make large impact on the project economics. So third is conversion to synthetic liquids. So this can be either hydrocarbon or methanol. And the fourth is some more unique products like solid carbon. And then you also have the zero carbon fuels like ammonia or hydrogen. And within each of these four categories, there's a wide range of specific solutions. So for something that sounds basic like power generation, there's alternative options for natural gas engines, there's microturbines, there's aeroderivative turbines, Stirling engines, and even organic Raikkonen cycles. So similar to the solutions in the other technology groups, these will all have advantages to different types of flaring solutions, like the variability of the feed gas flow rates, lower or higher hydrocarbon heating values, and the allowance of some components like hydrogen sulfide, carbon dioxide, and even the water saturation. So when we think about monetizing flare gas around 1 million standard cubic feet per day, or about 28,000 standard cubic meters per day, depending on your preferred units, there are some solution providers that have fully mobile solutions. And then there's also in this range ones with skid mounted solutions that are available and allow for quicker deployment once the facilities are available. Around the 3 million standard cubic feet per day range, or about the 85,000 standard cubic meters per day range, is when solutions start becoming semi-permanent. And this can require more than an acre of land footprint. And this, of course, changes the logistics behind these types of solutions. So my last comment I want to make is on the lead times and the business models for these solutions in today's global environment. So lead times for power generation can typically measure in the matter of months to maybe half a year, depending on the inventory. But for separation and compression solutions, it can be easily to a year lead times before delivery upon a purchase. And this becomes even higher a year to 2 years when looking at synthetic liquids or alternative fuel solutions. And then luckily, depending on the technology provider, some operators will rent or lease the equipment instead of doing a direct purchase, and even create gas purchase agreements where solution providers own and operate the field solutions, and then they end up buying the otherwise flared gas, of course, at a reduced cost.
Yeah, can I just build on Glen's comment too? So a lot of these options really are governed by where it is and what's available. So in addition to the options that Glen's mentioned, there's the option of just making sure that it's cleanly combusted. Right, and there's a lot of enclosed technology. And if I can just share a quick picture, it'll just show a non-routine pipeline blowdown that just gives you a sense. So this is something that can happen easily, quickly, and is starting to get used quite globally. And it's a quick example of just a pipeline blowdown, right? So as we look for options to do something useful with the gas, this could even be an interim solution. So what you see in the picture here is a pipeline blowdown in Texas. And instead of venting this volume, which is what is typically done, by converting it from methane to CO2, you actually reduce your greenhouse gas emissions 90% in a very easy, deployable, cost-effective way. And to Glen's point, it's mobile, right? So it can come in, do the job for a couple of days, complete it, and then move to another site.
And what is that for this perspective? Sorry, Glen. What is that, Audrey, for this perspective, the more benefit for the operator? If you can summarize. You mentioned mobile. What else?
Yeah. So first, it's very low cost to reduce the greenhouse gas emissions. And you can see in this picture, there's a lot of houses close by. Okay. So, right. So it's making sure there's no pollutants, because that creates a community concern. It's quiet. And one of the disadvantages with a flare, for example, is you have a lot of ground level radiant heat. So you can see in this picture, no one's moved their cars, people are standing by. And this unit is actually combusting about 5 million standard cubic feet a day.
Okay.
And
Glen,
right? Sorry.
Yeah.
No, go ahead. I think Glen is adding something.
Yeah, I wanted to build on what Audrey just said. Is a lot of times the reason why you need to get rid of a large amount of flare gas is bottleneck situations. And when you have bottlenecks, they're typically getting fixed. So the amount or the duration of the flare gas you need to remove is very short. Getting a point to market is a whole part of the monetization of flare gas. And when you can't do that for those short periods of time, which is quite common, then what Audrey is saying right here is an excellent solution, looking at those small durations as well. Thanks for adding to that.
Thank you so much. So moving on the operator side, I think, Clayton, you can give also another perspective that, of course, before to abate, we need to measure, and how the operator can move from the measure to the abatement. Can you share your insight on this?
Yeah, the hardest part about this, moving from, I'm very pleased to hear that you share there are commitments that countries and companies are making to eliminate routine flaring, and then moving from that to taking action is hard, and it's because prioritization is tricky. And if you're looking at large midstream or downstream facilities, whatever it is that you're flaring, you want to reduce that flaring, or if you're venting directly from equipment, if you're looking at midstream or downstream facilities, there are dozens of contributions, right? And sometimes it's hard to say, well, if we wanted to eliminate flaring or drastically reduce, there are dozens of different sources over the course of a given year that we have to address, and that's tricky. Conversely, on the upstream side, the issues that are causing venting or flaring, routine flaring, they might be simpler, and there might be a smaller handful of issues that we could point to, but there might be hundreds or even thousands of locations for a company, right? And so identifying how do we intervene, what are the right things to do, and I don't wish it upon any company to do what a lot of consultants recommend. My people that do the work that I do, we've done the industry a disservice where we say, here are all the sources of your emissions, now go do everything, right? And that's not smart, and no one's going to do that. So what we always work through is a marginal abatement cost exercise. Okay. And what you're doing in this exercise is identifying and quantifying what are the various sources of emission. So in a midstream or downstream facility, if you have one large flare or a small handful, what are the contributions over the course of the year, and quantify to the best of your ability. You may not have accurate measurement on those, so sometimes there's a little bit of investigative work that's entailed with that. But in the course of the year, what are those sources, and then what would it take in order to eliminate those sources? And sometimes these are costly. And so one example would be vapor recovery. If you have a vapor recovery system that operates at 95% effectiveness, that's pretty good. In order to get that next 5%, you have to put in a fully redundant system. So you may not have to increase your cost by 100% to do that, but there's a significant cost to get that incremental 5%. But that is worth exploring, right? On upstream systems, normally the issues are simpler, but there's a larger number of them. And so the magnitude of each event varies greatly depending on the production from that site and the unique characteristics of that site. And so the technical solution might be the same across many sites, but the emissions impact will vary from site to site. And so very carefully quantifying what are the opportunities for abatement, and then coupling that with what would the cost be to remove that. Then you can generate a marginal abatement cost curve that will show you here all the potential abatement opportunities and where they fall in a metric, dollars per metric ton of methane or dollars per CO2 equivalent, whatever metric you want to look at, whether you want to look at that over a 1-year period or a 5-year period. And then what we like to do along with that marginal abatement cost curve is to add a tornado plot which shows the magnitude. And so when management sees on one side the marginal abatement costs, what are the opportunities where there's a low dollars per metric ton of CO2 equivalent or methane on one side, and then what are those handful of projects that really move the needle, that have a large magnitude, that becomes an effective decision-making tool rather than a consultant coming in and saying, hey, execute these 800 projects. It turns into, hey, we think these 20 or 30 projects are going to be the most effective and are going to meet your metrics and they're going to move the needle.
Thank you so much. So I think we discussed with Audrey and Glen about small size. You mentioned also large size. So let's remember some data points. So we are talking about for the small size, we are 40% of flared amount of gas worldwide. This is the data coming from the World Bank. But there is also the amount of flare that are large flare. 10% of the amount of the total gas are in the large flare system. Again, you mentioned, Clayton, business case and return on investment. So these kind of things are very crucial. If I can highlight in terms of impact and evaluation for operators. So in this scenario, it's not a matter just to abate emission, but also to understand what is the return of investment associated based on the availability of the data. So let's move on small source and be focused on the small source. So, of course, when we talk about small source, it's difficult, or let me say, very challenging to be monetized. But we already introduced a concept of how we can, let me say, think about overall emission, not just the big size, but also looking the small amount that can affect. Let's restart from you, Clayton. So one of example of the small source and the engineering solution that we can apply is vapor recovery. So from your experience again as a designer, what are the recommendations to apply this solution? Where, how, and everything that you can share?
Right. Yeah. Vapor recovery it's very difficult to get it exactly right, but it's also very important. And so the technology has come a long way. I think one of the most important aspects of getting vapor recovery right is getting the right technology right. And there are a lot of companies that manufacture equipment that will do this. But smart system integration and a really effective vapor recovery unit that's not integrated in a smart way into the system around it. My analogy would be if you had if you wanted to put a Formula One engine in your car, and you just buy this really sophisticated engine and then just throw it in your car, but don't think about all the linkages and everything happening upstream and downstream, that engine's not going to be very high performance. In order to get a really high performance engine in your car, a lot of things have to be working right, not just the engine, everything around it. And vapor recovery is no different. And so when I see vapor recovery not operating effectively, it normally has to do with the way the system, 3 steps upstream and 3 steps downstream, has the whole system integrated and smart controls around it. There comes a point when vapor recovery is not effective, and actually vapor recovery, it sounds bad to say, but vapor recovery can do more harm than good, and I see this a lot in our industry. And I'm going to share a very quick visual. One point I like to emphasize when it's dealing with small sources, whether you're implementing vapor recovery or you're making the decision to move away from vapor recovery and move towards abatement. I think a lot about process variability, and a lot of times vapor recovery units are put in based on average flow rates. And so if you think about the green line right here would be an average flow rate that either a vapor recovery unit or a combustor flare is sized for, but then the red is the process condition that it gets from moment to moment. And that could be flow rate, could be pressure, temperature, vapor properties, any kind of fluctuation in any kind of process variable. And then the purple becomes some kind of uncontrolled emission or something that's not ideal. And so the first thing we want to do is, if we're building new systems, we can build a green line that's way above the red line and just make it robust for all that variability. When you're dealing with existing systems, though, you don't always have that luxury because you're dealing with declining assets and you don't have a lot of money to spend. And so what we like to focus on is reducing process variability and moving to something like this. How can we flatten out the process, right? And so a lot of times, so moving the red line down, which is, again, your process variable, could be flow rate, pressure, temperature, and moving it to where it's more in line with what the system is capable of, rather than spending a lot of money moving the green line up. How do you reduce that process variability? Not only do you find more cost-effective solutions, but your equipment will run more effectively anyway, right? So one thing, I mentioned this earlier, consultants that do the work that I do, in some ways we've done a disservice to the industry. One of the things that I don't like to say is, or something that we shouldn't say, is implementing vapor recovery is good business and you should do it, recover more vapor and put it in the pipe and sell more product. Again, because there are times when it does more harm than good. If you put in vapor recovery in such a way that you're having to hold back pressure on atmospheric tanks, for instance, that can be done effectively. But if the amount that you're recovering is not commensurate with the increased probability of venting from those tanks, then over the course of a year, what I see in many cases is an increased amount of uncontrolled emissions. You can have something that operates 95% effectively, but that 5% when it's not, and you get uncontrolled emissions, it can greatly outweigh the benefit from what you recover, because Ilaria, what you mentioned earlier about methane being 80 times the effect of CO2, so that direct emission can outweigh. And so I encourage people to think very carefully about systems integration over the course of a year, not just average flow rates or not just a slice in time. How will this work? But how's this working over a long period of time? And how do we maximize, or minimize, as it were, emissions, looking at the entire system over an extended period of time in a smart way?
Yeah, if I can add to what Clayton said. So sometimes when you look at the size of the volume and as Clayton mentioned, looking at the economics and the feasibility, in some of those situations, especially for low volumes, it may be better to just make sure you're cleanly combusting it. And there's lots of enclosed technology that, that will allow you to make sure you've got high reliability. This equipment can be tested to verify that its performance is there. And in the US, for example, the EPA has test procedures, has test procedures that show you that the equipment that you're purchasing is performing to a high efficiency. So the minimum in the US is 95% efficiency for an enclosed combustor, but there are units that will deliver 99.99% performance as well.
Very interesting number. Glen, but based on all your experience, which kind of technology suggest for this application?
So I guess that Clayton definitely hit on a couple of really good points. One of them being that you want to look at optimizing or working with the facilities first, excuse me, so that you don't have a changing solution once you've gotten to the gas recovery, and then you start optimizing your process second. You might need to change the solution you're looking at. And then the other one is looking at those general abatement curves and saying what is the best technology and the most economic as well as safe. Because again, you don't want to do any damage to your process and you want it to be able to fail safe. So when looking into these small source technologies, we usually start by setting up a matrix of the vented sources versus the local points where it can be sent. And depending on the location, these recovery points can be limited to compressor suction inlets in a stranded field, or become more plentiful in a situation like multiple facilities in a stranded gas field, or sorry, in a gas treatment plant. So either way, there'll be some potential for the boost pressure as well as a treatment. And treatment of small volume gas can become a real economic deal breaker. And same with a large amount of boost pressure. So any chance to send the gas to a location where the treatment is not necessary is preferred. And in that case, it would be like taking sour gas with CO2 and H2S and putting it into the front end of an amine plant. So with or without the associated treatment, the amount of pressure boost starts defining the required equipment. So small compressors, potentially in multi-stage, are always an obvious solution, but there is also a lot of potential with systems like adductors or ejectors. And these units work by taking a high pressure vapor or liquid working as a motive, and they usually boost the the emission gas pressure. And there's usually, the potential of a large pressure letdown within the process. And in these cases, you can use that to boost the emission gas, and then you're using potentially wasted energy. And when it comes to the different flow rates, you can always recycle back some of the gas, keeping the amount of motive and emission gas going to the adductor or ejector consistent, so it has a continuous performance. So the last thing that I wanted to mention on is multi-phase pumps. We've seen a lot of success with these types of units, along with multi-phase metering devices if it's necessary. And those allow the vapor to be sent with the liquids to larger gathering locations. And then in those larger volumes, you play with the economics for the scaled solutions like the ones that we've got inside the flared section that we talked about previously. And or the pumps can get the vapor to locations where the pipeline takeaways and stuff become accessible and they take over.
Thank you so much. So I think that we discussed about a lot of operators, efficiency, recovery, and I would like to say also return on investment. I think a key player also is technology. So, and research and development. So Audrey, that probably is your space. What are, let me say, the insight, especially for small sources that are difficult sometimes to address? What are the tips and insight that you can share for this?
So when we start to look at sources, I really like the comment, start with, the comment that Clayton made, start with your biggest stuff first, right? It's the 80-20 rule. But we know that as we tackle some of the bigger volumes, we've got to tackle some of the smaller ones. And I'll pick, for example, methane slip from engines. It's a low volume. We've got a lot of engines. Every molecule of gas gets moved, has an engine and compressor behind it. We know that the flue gas off those engines has a bit of methane, but it's low volume, it's high temperature. So one of the solutions that we've been working on in partnership with Stanford and Johnson Matthey is looking at a catalyst. But not only do we need to deal with the methane, but we've got a real opportunity with the heat coming off that stream. So what we're working on right now is being able to use the catalyst to get rid of the methane. Because we've got a lot of heat coming off this engine, there's an opportunity to take that heat and convert it to power using an organic Rankine cycle. The beauty of that is you create a revenue stream. And so that offsets your costs of dealing with the methane. And we can see opportunities globally wherever you get rid of methane, if you can use that energy or that heat, you actually can get to net zero for net zero cost. When you start with carbon dioxide as your way of getting to net zero, you can't create any revenue. But the beauty of starting with methane is you can create a revenue stream that does eventually allow you to get to net zero. And in the example I talked about, for example, converting methane to CO2, even though you're creating another greenhouse gas, because you've reduced your GHG emissions 90% in a cost-effective way, that remaining 10% can be sequestered or isolated or used to make product, but the cost is covered by the revenue you created from doing something useful with that energy.
Very, very interesting. Thanks. Thanks a lot that you're sharing. So I think we'll land on the second part. So I will ask the audience to be active in the discussion. So I saw there is one question, but I would suggest also the others to pose the question, because we have a great opportunity to have experts and panelists here. So this is a great. So I will start with Valeria question. And I think this is something that all of you can answer. So what do you recommend in terms of methane abatement technology for offshore location? So, and mainly because we are challenging, offshore is very challenging, especially for process perspective. I don't know, Glen, or let me say,
Sure.
Clayton, if you want to start.
I can take a quick shot at that. I think that when you look at the abatement for offshore, one of the things that we always look at to start is what are the utility requirements at the offshore platform. So one of the things that you can always look at is what do you need there? Is there anything inventory-wise that you're purchasing and pulling into your platform? That's a good way to start looking at what potentially you can create. And Audrey was saying it well, that you have the potential with methane. It's not just CO2, it's a hydrocarbon. It has a heating value. It might become something like a fuel gas that goes to some of the heating that's required offshore. But we always have to keep that mental mindset that in the future, the far future, maybe if it's going all towards electrification, then we don't want to do solutions that might be phased out in a couple of years. But really, it does come down to the fact that we're dealing with a hydrocarbon. It has value to it, whether it needs conversion or it just needs to be burnt or burnt efficiently. And that's usually where we start, with the one caveat that we're also looking at the footprint of the technology and the weight. So when it comes to offshore, there are solutions that are excellent, but they have a weight and they have a footprint that's not really applicable to the situation. And now we've seen some technology companies working with barges that could be set alongside with flexible hoses to get away from that constraint. I hope that answers the question.
Great. I think that you give us a broader perspective. And for this, I have a personal question that probably I will pose to Clayton. So we are talking about efficiency, electricity, small, large emissions. So we are talking about a broader capabilities and skills. So it seems probably required also some consideration about organizational and capabilities. Clayton, what is your perspective? How the company need to move for this in order to be fit for purpose?
Yeah, no, well, Glen brings up a good point, and you're right, it does bring a broader perspective, because I start out so in the weeds on device by device, but yeah, you're right. I think companies, especially when you talk about scope 3 emissions, if you're buying electricity, having the right resources and the capabilities in house, they understand that and analyze it, and take a really critical look at what energy are we consuming and what is the impact. And now that companies are reporting that, and that is a part of your emissions footprint, right? And then if you're in, some companies are moving towards generating power, so there actually are situations where companies can self-generate power themselves, whether it's direct generation or as Glen mentioned earlier, organic grain cycle through waste heat recovery. These are technologies where there's some overlap between the skill sets we have in our industry, but it's not something that these technologies is not something that you can just take the people that we have and just directly translate over. So there is a learning curve in our industry, and there is also something that we need to do with going out, going to other industries and bringing people in so that we're supplementing the capabilities we already have with knowledge that's already being gained in other industries, right? And I do want to add a quick point on the offshore, the question about abatement, and Glen's right, footprint and weight. I wish this were an easy answer. I've worked offshore in the Gulf of Mexico, and I've been lucky enough to visit other offshore locations in other parts of the world, and it's we all know it's easier said than done to just say, oh, put in redundant systems or put in extra vapor recovery or whatever, or switching to more efficient compressor drivers or things like that. And even if these things could be done, sometimes it takes years, right? And I'll go back to the idea of reducing process variability and looking at things like oil. One example, the oil stabilization unit that had erratic operation. It was stabilizing the oil and everything was working completely fine. But when you look at what it's doing moment to moment, there are erratic swings because a back pressure control valve was undersized. And so as a result of that, that led to more volatile oil being moved in the pipeline, and then occasional swings where a line to flare would occasionally open to prevent a PSV from opening. Well, proper sizing and tuning of that controller was able to line out the operation of that unit so that you didn't have the higher oil volatility, and you didn't have those occasional upsets where the line to flare would open up. And sometimes these opportunities are hard to look for, but really diving into the data and really thinking about, okay, what are the things I can do without changing the footprint, without changing the way, without spending years of planning or taking a shutdown. Shutdowns offshore can be extremely costly. So what are the things that we can do in that regard to move the needle? In addition to that, I would say taking a hard look at what are the flare technologies, right? So if you can get, Audrey's brought this up, if you can get your flare might be compliant with whatever regulations you're compliant with. If you can get that extra 0.5% or 1% destruction efficiency, there are flared emissions that are unavoidable. What we can do is get that extra percent or some incremental amount from a slightly better flare technology, and those are things that they can add up over a long period of time. Yeah.
Thank you so much. I think Simon asked a question about the destruction. I think I take for you, but also for Audrey and Glen. So could you talk more about the performance classification for methane destruction equipment that was mentioned? I think you mentioned it as well, but please, if you can give more details that Simon is asking for.
Actually, I'm going to defer to Audrey on this. I think, Audrey, you have more expertise in this specific area, if that's okay.
For sure. So one of the challenges, we use destruction efficiency and combustion efficiency interchangeably, and really they are two different things. When you talk about destruction, you're really saying, look, I'm destroying some of the bonds, but it doesn't necessarily guarantee at the end of the day what's the final output. So when we look at it, if we truly want to abate methane, we want to make sure that we're turning it into CO2 and water. And so that's where combustion efficiency comes in. One of the challenges with a flare system is, how do you measure that efficiency? And some of the work that we've been doing, looking at efficiency with drones, etc., we also see that the flares are heavily influenced by wind direction, size of droplets, lots of different things. So it's actually not one number. And as wind changes, that efficiency can sometimes change as well. So as we look at, truly being able to quantify the greenhouse gas emissions that we've reduced, being able to say with clarity that we've converted all that methane to CO2 and water becomes extremely important. And of course, looking at enclosed technology that you can control your combustion process, you're not as influenced by wind, starts to play a really important role about that. So I hope that helps.
And one thing I could maybe add to that as well is that sometimes when you're looking at some of like the open type destruction, like flares and stuff, you have the wind to deal with, but also sometimes what people think they're running and operating at is less efficient instead of more efficient. So a good example I always hear of is the flare's smoking, it looks terrible and everything, so they start adding more steam, and then the smoke comes down, the flare's smaller, it looks better, and so they add more steam, and they keep on adding more steam without realizing that what they're really doing is stopping the combustion of the hydrocarbons, and then therefore you're releasing a whole bunch of methane. It's a much worse emission footprint, but again, from a PR point of view, you don't see the flame and such. Audrey, when she was talking about the enclosed technology, it's a nice gentle glow instead of an open flame. So sometimes you can get the best of both worlds. You can get, small visibility, small radiation footprint or radiant heat footprint, and good destruction efficiency. But again, with things like supplemental steam or such, sometimes when you think you're doing the right thing, you're actually not. And you can also go to monitoring solutions. So solutions that will look at it, maybe not continuous, but at least snapshots to say, am I doing the right thing? And what do my construction or combustion or destruction efficiencies look like? So you get a good idea of that true emission footprint. Thanks.
And just to add to what Glen said, so the other advantage of using an enclosed system is you can actually recover the heat, right? And so not only can you guarantee an efficiency and measure it because you're in an enclosed system, but it creates a great opportunity to do something useful with the heat. And so, for example, it could be used to generate power using an organic Rankine cycle. It could be used to treat water, or it could simply be used for process. And once again, all those options give you a chance to generate a revenue stream, which you wouldn't get with a flare, right? Because it's very hard to capture that heat. It's very hard to measure its efficiency. And it's becoming, according to the World Bank, and this number really surprised me, every day we flare and vent over 14.5 billion standard cubic feet of associated gas. That's a phenomenal amount of energy, that we're wasting, but it also is an enormous amount of methane. And it's happening in areas where actually people live without energy. So some of the projects that we're starting to work on in these international areas is first, let's make sure we're cleanly combusting the waste gas so that we're not having a negative health impact on communities that live close by. And because we can pick up that energy, it could either be power for the community, it could be and one of the examples that I use a lot is Nigeria. Here, it's heat to dry their food. They've been drying food in the heat of a flare, for example. Or it could be used at a site as your process heat instead of a heater or or burning more gas in a boiler. I think building a bit on the other question you asked, and what kind of skills do we need into the future? And, Clayton talked about it. I think the skills we need to add to is starting to look from a system perspective, not tops down, but bottoms up. When I look at a compressor station, what can I do to manage my methane emissions? So bringing in this skill set that takes a more holistic view of what's happening in emissions. I think right now we're still very much in this reactive world where we'll fly a drone or we've got a handheld and we're going, oh, we've got a leak, and we send someone to go fix it. But I think as engineers, we need to start to look and say, we know we've got emission issues. We know we've got methane issues. What can we do differently at a well pad site? What can we do differently at a compressor station? What do we do differently with a pipeline?
Yeah. Let's move a little because I saw a question and thanks a lot for audience because it's pretty active. So we have tons of questions. I don't know if you have time to answer everything. So we try offline. So Franca mentioned fugitive emission. So we mentioned small source, but let's talk about fugitives. That is another big category of methane emissions. So how can think about to minimize those emissions during the building and the design of the new plant? Any insight for this?
So one of the things that we look at is we have a pretty serious situation where our divisions are looking into the technologies. In this case, we're talking about technologies to abate or to vapor recovery. We have quite a big section on monitoring. And when you recognize where leaks are coming from in the industry and where those tricky points or those sticky points are, one of the things that it leads to is that understanding. So are there certain parts that break down? Are there certain, pieces of equipment that tend to have the fugitive leaks more meaningfully and more frequently? And once you have an idea of those types of leak spots, then when you're looking at a green location, then you can start already on a good foot. Brownfield, unfortunately, you have to look at cheaper situations of maybe not replacing equipment, but fixing equipment. But in a green field, you have the opportunity to say, what are all the things we've learned from the monitoring of methane leaks? Let's find out the associated equipment problems, and then let's do it properly from the start. So that's one of the things that we look at is what can we learn from brownfield experience? How can we apply it to greenfield?
Yes.
Of course, you need a lot of data, a lot of facilities, a lot of work, but that's part of it. And OGMP has a great situation where they have that voluntary program to do all the top-down, bottom-up type stuff. So that's a great beginning of making that database to understand how to build the next facilities to prevent that leakage and fugitive.
Clayton, your perspective as a designer.
Yeah, designing up front and operating, the questions about design, of course, the obvious answer on when you're operating would be just more frequent inspections, right? And that I think anyone could come up with that. Yeah, on design, I think Glen's right. Taking a hard look at what you've learned from your brownfield experience and where your mission is really coming from. More and more people are choosing. So we do a lot of prefabrication in our industry, and we say, well, let's prefabricate as much as we can off site. And so when you get to site, you have a lot of pre-flanged pipe and valves and everything that comes out. And I'm getting more and more clients that say, well, we want to prefabricate some, but let's seek that in moderation. We want to do more stick building, not, easier said than done offshore in a more constrained environment, but they do that so they can reduce the number of flanges, right? So they want more direct welds, on long runs. So, if you got a long above ground tie-in or flow lines or interconnecting pipe, how do we reduce this number of flanges so you have fewer leak points? Now, what that means is not eliminating prefabrication, obviously, but nudging away from prefabrication and a hybrid of stick built and prefabrication for that reason. So that's one example, I think, of what Glen's talking about. Like, well, if we see that, flange gaskets, and, these sort of problems leading to emissions over a long period of time, and there's a very large number of them, especially onshore environment where you have hundreds of sites and each site has hundreds of flanges, right? That's a lot of inspection and repair points. That's one example, I think, of what Glen's talking about. We're using that experience in brownfield to translate into a slightly different approach on how you design and build.
Amazing. I think a lot of inputs today. So I love one question that is a little bit, let me say, specific for one sector that, of course, methane is applicable. So Chinedu asking, what would be the recommendation for site such LNG where methane serves as a feed gas but potentially suffer fugitives emission as a key impact on their footprint? So again, fugitives, but specific for LNG. So I don't know if you have any insight for that.
So I can jump in a little bit on that. So there's lots of different places for fugitives, but one of them is in filling. The vessel is the vapors that get displaced there. So it's vapor recovery units, maybe it's cleanly combusting it, but paying attention to all of those little methane emission fugitives that of course increase the carbon intensity of that LNG molecule, right? So once again, it's, if it doesn't make sense in terms of vapor recovery, then make sure at least it's cleanly combusted, so that you're not putting any of those methane molecules into the atmosphere. Yeah,
you're right. And of course, in LNG, there are a lot of examples where, mainly for return on investment, the methane emission are recovered in order to be effective. So I think we have time also for another question and for close out. So because we have 7 minutes before the close. So let's take the OGMP one. So Morrison asked, what significance will OGMP 2.0 bring in terms of change in environment monitoring in hydrocarbon processing plants and offshore installation, especially regarding venting and flaring? So I think this is a big topic. Let me say cool for our word, but let's go around and ask you what is the significance for OGMP 2.0. Audrey. I know that you can bring a lot of insight in.
So I think it's going to push us very much to pay attention to how we operate our facilities. And I think at the early part of the conversation, I talked about this routine and non-routine. We haven't talked a lot about the non-routine, and I'm going to pick on a compressor station, for example. We know when we put that compressor station in that the engine manufacturer tells us after so many hours we've got to do maintenance. Typically, if it was attached to a compressor, we would vent all that volume to do maintenance. Is this routine or non-routine? Number one. But I think these new rules are now going to force us to look and go, you know what, that's not acceptable anymore. Because if you start to look at sites, a significant portion are coming from, for example, maintenance. But also, what if that engine goes down? The field operator will usually start it without a load, which means they would vent what was in the compressor. So building on Glen's comment, we need to start to look at reliability of engines. Look at, you know, how often do they go down? How do we design our site to make sure that we're not flaring and venting? And we had a chance to work with one of our clients, a large midstream company, who were in New York State, and they were told they cannot flare and vent anymore. Otherwise, that compressor station needs to get shut down. So they were able to create a zero flaring venting site. So I know that this is possible. And so I think the new rules are going to push companies more and more to start to look at how they design facilities. So I think it's a good thing.
Great.
I think just building on that, I think it'll also keep a lot of operators and companies more honest, because there are some kind of, you know, accepted amounts of destruction efficiency and stuff that they've been working with for a while, and a lot of companies are saying, oh, that's a great number, we'll take it. And I think at some point in time, it really has to be more realistic and saying you really have to know your numbers. And I've seen some different regulatory boards saying, okay, those numbers, the assumed numbers should start going down, and then it'll be more impactful for companies to say, no, we can prove that we're doing better. But right now, it's almost the other way around. Something like OGMP really calls to play the honesty and the transparency of how you are really running your facilities, and what Audrey was saying about the maintenance of equipment, things that, you know, should be done, but maybe is not being done out of convenience or monetary benefit. Those things are really going to be pushed to the forefront for the better, for emission reduction. And also you're going to be having a better performing process, which will be good in the end. But again, it just pushes that economic need a little bit ahead of time.
Great. We hope, Clayton, for your side.
Yeah, I agree with everything these two are bringing up. And you know, whether it's OGMP or in the U.S., our Quad O regulations or Subpart W. I know most of the audience is not in the U.S., but I think they're indicative of what's coming. In the past, either our Quad O regulations or our reporting structure, you know, they would look at certain devices and say, well, how many of each type of device do you have, right? And you just you just add up reporting numbers based on that. And now what they're saying, there's more and more of an emphasis on, are those devices functioning the way that you say they are, and it's actually good for operators, because it's a little bit of a carrot and stick, but it creates an incentive to actually inspect and maintain and validate that and document that these devices really are working the way they're supposed to be, rather than just saying, well, you got all these devices, we're going to assume a worst case scenario for how they're malfunctioning, how much methane they're emitting. And so with OGMP, that's what I see. Well, the other aspect of what's going on in the U.S. is more measurement. How much are you sending to the flare? If you say you're recovering vapor from your VRU, what does that look like? Show us the temperature from your flare. You need to have a thermocouple, not just a status on a pilot, but a thermocouple. You have to share that. And so I think it's going from, you know, bland assumptions about industry-wide averages, and then here's how they apply to you. It's going from that to know your specific instance. Is your plant, you know, whether it's upstream, midstream, downstream, doesn't matter. Is it operating the way that you say it is? And then if it isn't, what actions are you going to take? And even with the super emitter program, I mean, that's the next step. Here in the U.S., you know, there's a very low threshold to meet this super emitter volume. You know, if you have a certain leak, a certain amount of venting per day, it's actually super emitter is a very low threshold, right? And what it pushes people to be able to do is say, one, avoid those, but two, if they do have those unfortunate events, be able to prove that they were short duration, rather than assuming, well, here they were, you know, that event took place since the last inspection or since the last time someone, you know, intervened with this piece of equipment. And so I welcome it, whether it's OGMP, whether it's voluntary initiatives or certification programs or regulations that move us in the direction of measurement and monitoring and verification of how things actually are working.
I think so. We can only say wrap up the discussion. So wonderful. I would like to add just that we discussed about data, type of emission, insight, design. So a lot of insight, and this is an example how broader and complex in some way is this topic, and how much we can learn every day on the discussion. So amazing for my side. I would like to thank you, the panelists, for their insight and their contribution. I think we have a lot of questions also that we need to answer. Probably we can follow up offline with the mail or with other systems. So thanks a lot again to come here. So I think just the closing remark, we are approaching the COP29. And of course, this is a big topic for everyone, and we would like to be active on this. We are in this space and we are trying to push our knowledge, our awareness in order to create more awareness as well on the topic. So thank you so much. I would like just to leave the audience to say that thanks a lot to join us and to participate actively. So it's a pleasure to me, was a pleasure to me to moderate the panel and to have those great people here. I would like to suggest also in September, October, the Methane Guiding Principle will organize another interesting technical webinar related on drones and monitoring as well. So please keep in touch and look our post, because will be very interesting as well. So I would like to thanks again Audrey, Clayton and Glen for the insightful discussion, and I hope that we can connect again on this topic that is important for all of us. Thank you so much.
Thanks, Ilaria.
Thank you, everyone. Pleasure to
Thank
be
you.
here.